Question number 2. Concentrated sulfuric acid reacts with alkenes, alcohols and sodium halides. Name the mechanism for the reaction of concentrated sulfuric acid with an alkene. So the double bond attacks the sulfuric acid and the sulfuric adds on, so it's electrophilic addition. We'll have a look at that mechanism now and understand electrophilic addition. So what actually happens here is the double bond attacks the H+. That's because that's a polar bond. Oxygen is more electronegative than hydrogen, so it gets a delta minus, and the H gets a delta plus. So the electrons in the double bond to that H. And then the electrons here move onto the O because the H is bonded onto the alkene, so the electrons move onto the O. That's going to create an O minus because electrons have moved onto the O, so it creates a minus charge, and there's a pair of electrons there from the bond on the O. There's a plus charge here because the hydrogen is added onto the end, so this is the major product. So the hydrogen, will it go to the left-hand carbon or the right-hand carbon? It goes to the carbon with the most number of hydrogens to leave a stable secondary carbocation. That carbon is charged plus because electrons have moved away, and that carbon is charged plus also, you could say, because it's not got enough bonds and electrons are in bonds, so it's short of electrons, it's short of minuses. So it's got a plus charge, and that's a stable secondary carbocation. The C with the plus has got two other carbons bonded to it, so it's secondary, not primary or tertiary, and it's stable because the two methyl groups repel electrons and reduce the size of that plus charge. Now the lone pair of electrons from this ion that's made attack the C+, and it bonds on like this. This is an electrophile and an electron pair donor. Here, an electrophile, and because two reactants have made one product, two become one, and therefore it's addition, electrophilic addition. Draw the structure of the minor product, the reaction between concentrated sulfuric acid and propene. So instead of the H bonding to the left-hand carbon and forming a stable secondary carbocation, as normally happens, the major product, it could, in theory, a small amount could do the opposite. So the H could bond here and leave the plus on carbon number 1, and the OSOOOH could bond onto carbon number 1 instead of carbon number 2 via a primary carbocation. That's less stable than the secondary carbocation, but it could occur in small amounts, and that's called the minor product. So here the OSO3H, or you could draw it out like this again, but instead of it bonding the OSO2OH, instead of bonding to the C carbon number 2, it's bonded to carbon number 1, and then you've got CH2CH3. Explain why the product in your answer is the major product. So we've said that already. It's a stable secondary carbocation. It's more stable than the primary carbocation. If you were to make incidentally a tertiary carbocation with 3 carbons around the C+, that would be even more stable, because the reason why the methyl groups repel electrons. It's called a positive inductive effect, and it reduces the size of the charge on the C+ and makes it stable, but all you need to say is that the methyl groups repel electrons. Butan-2-ol reacts with concentrated sulfuric acid to form a mixture of 3 isomeric alkenes. 2 of the alkenes are stereoisomers. So let's have a look what happens. Well, first of all, butan-2-ol looks like this. And what concentrated sulfuric acid does is it removes water. It removes an OH, and from a neighbouring carbon it removes an H. So the water is coming from here, an OH, and on a neighbouring carbon an H. It could do it the other way. It doesn't know left from right, so it could take an OH from this carbon and an H from carbon number 3 instead of carbon number 1. So it can take the HOH from here in between carbon number 1 and carbon number 2, and that will leave a double bond then in between carbon number 1 and carbon number 2. It will make but1ene. Or alternatively, the OH and the H could come from carbons number 2 and carbon number 3 and make but2ene. And but2ene would then have stereoisomers, geometrical isomers, E and Z isomers. So let's have a look at the skeletal formulas. So I could have but1ene, where the double bond is in between carbon number 1 and carbon number 2, but1ene. I could have but2ene, and I'm going to have 2 forms of that. I could have butyene, which would be E-butyene, and I could have Z-butyene. So there's the double bond, and here's the methyl group 1 on one side and 1 on the other, and here is Z-butyene with the 2 methyl groups going down on the same side. You could have them going up, so you could draw this in any kind of shape you wanted to. As long as the methyl group's going up and the other one's going down, you could have it this way, down and then going up if you wanted to, and similarly you could have both of these going up. As long as there's the 2 methyl groups are on opposite sides of the double bond for E-butyene and on the same side of the double bond the Z-butyene, that will get you the marks. This is a little known thing, but concentrated sulfuric acid can act as an oxidizing agent, so it can turn butan-2-ol into a ketone. Now the best way of doing that is through acidified potassium dichromate with a little bit of dilute acid. That would be the best way of turning a secondary alcohol like this, a secondary alcohol with the COH in between 2 carbons. So the COH is bonded to 2 carbons, so that as a secondary alcohol with potassium dichromate and a little bit of sulfuric acid would turn that into a ketone, a C double bond OH, and that H would be released. Similarly, if the OH were at the end on carbon number 1, it would, a primary alcohol, it would make an aldehyde, and then further reaction with potassium dichromate heated for a prolonged time called reflux would actually turn that then into a carboxylic acid. So the best way of oxidizing a secondary alcohol into a ketone or a primary alcohol into an aldehyde and then into a carboxylic acid is to use acidified potassium dichromate, which would go orange to green in the process. However, a little known fact is that concentrated sulfuric acid can do that on its own. It's not as strong an oxidizing agent as acidified potassium dichromate, but it will do it. It will do it to a slight amount. So you could get, just with concentrated sulfuric acid on its own, it needs to be concentrated sulfuric acid, and as I say, it's not as strong an oxidizing agent, it's not going to do it as well as acidified potassium dichromate, but it could turn that into butan-2-ol with a butanone, butan-2-one or butanone. It can only be an one a ketone, it can only have a carbon to oxygen double bond at carbon number 2, as if it was at carbon number 3, you'd just start labelling from the other end, that would be butan-2-one as well. So butanone, we can make that. The role of the sulfuric acid, well, it's removed H's, it's taken an H off there to make a C double bond O, it's taken an H off there and an H off there. Something that removes H's is called an oxidizing agent. And how you would separate then a byproduct, well, if you've got more than one liquid, you'd use distillation.